Okay, well, it's really fun to be back. Yeah, kind of knew I wanted to come back and see my friends, but it's been a really fun experience to get to hang out for the past couple of days. I wanted to take this opportunity to talk a little bit about this sort of experiment that we've done at scale. I want to talk to you about how I think that our experiment has interacted with the local community where we conducted the experiment. And then, moving on down the line, I'm going to think a little bit here out loud with you guys about how do carbon credits actually potentially for using money earned from the sale of carbon dioxide removal, which we'll go into, but how can that underwrite programs that I think actually can help people? And then if they actually do help people and are sustainable in that sense, then I think that we can keep making agricultural interventions like this that have the potential to be massively carbon negative while actually having a pull from people who need things like food security. It's a little bit of an important one. So this is the obligatory, that's not a stock photo, I took that photo. So if you're judging me for it, it's not stock, I took it. But what I want to think about is basically this other part of the food supply chain that, me as a Westerner, I didn't really interact with it at all until recently. There are more than 500 million smallholder farmers worldwide, and I've defined that as people who tend to less than an integrated total of 10 acres. So that's not a whole lot of land. Those people produce 1/3 of the global food supply, and that's actually eaten by a little over half the people. So half the people on the world are supported by that 1/3 of the food supply, which obviously has implications for feeding billions and billions of people. And then sort of the growing challenge here is that in these regions that are resource limited, where lots of food is being grown year on year, there is essentially access issues to agronomic inputs that help people grow crops efficiently, right? So I pointed out that 1/3 of the global food supply, but that feeds half the people. So that's sort of showing you that there's a yield shortfall compared to what we enjoy here in the West. And so you kind of roll that all up together and you have these people who are farming more degraded lands, and now that we've got climate variability and more extreme weather events kind of coming on the horizon, those folks are correspondingly more vulnerable for some of these climate calamities that I would argue they're in no way responsible for at the same level that maybe I would be. So I just kind of want to show you, this is from the UN, and there's just been some broad strokes, high level sort of policy documentation that's been put out to try to help people think about framing this type of question. And I'm going to focus mostly today on Asia. Monty does do a small amount of operations in sub-Saharan Africa, which I'd be happy to talk about maybe as a sidebar a little later. We will focus on India. But there's two main problems here which I want to draw your attention to. One of them is soil acidity. So in soils from monocropping, growing food year on year, the essential mineralization of the soil can get out of whack. You end up with a bunch of residual protons on surfaces and other places like that. Or even worse, left over, you can have nitric acid from leftover fertilizer residue that actually makes nutrients difficult for plants to obtain. So addressing nutrient imbalance in soils while simultaneously addressing soil acidification from overuse are pathways towards actually being able to have an entry point into managing these agricultural lands in a different way. Does that make sense? I like interruptions, so I'm going to interrupt myself. All right, cool. So that's sort of the premise, right? We've got some fields that are pretty beat up from overuse and, for lack of a better way of putting it, being undertended by fertilizers or things like agricultural lime that are typically used in the West to boost crop productivity. So I'm just going to kind of motivate this to make sure we really beat a dead horse here. But what I want to do is think about, there's this opportunity that comes from that cropping shortfall. And so these restorative practices, if there is one, if there is a crop intervention, is there something that I can do that will help farmers grow an even incrementally larger amount of food in their managed land? And then if we have improved soil function and improved soil health, that's actually a bigger safety net for those farmers. But then this is like, that sounds great, but then it gets kind of hard. It's like, if this takes extra work, who's going to do the work? If, I was going to say, hey, it'd be great if you put fertilizer on this field, you grow more plants, right? Well, someone has to go pick up that fertilizer. They have to spread it. They have to pay for it. So the question is, who's going to be the labor force that helps you over this barrier? And then at the end of it, it's really, the bottom point here, minimizing cost and complexity for farmers. That's, code for who's going to pay for it. Who's going to help out a smallholder farmer that, might not seem to have much economic upside to investors in the West. All good? Okay. So this is the crop intervention that we at Maki have primarily engaged with. And so there's this idea of farming with rocks. We'll kind of go from left to right here. So this big pile of basalt dust here is, it comes from primary crushing of railroad ballast and building roads out in India. So there's massive flooding sites throughout the entire center of the country. And it's actively being used for modernizing travel and transportation infrastructure. And what ends up happening when you smash rocks? Does anyone know? If you're trying to make railroad ballast, a bunch of rocks about yay big, and you start crushing it up in a cone crusher or something of that nature, you end up with a bunch of dust that's too small to actually be used for the construction. And that typically turns into these big mud piles, right? And someone actually kind of wants an intrepid young group of folks to come pick this stuff up and try to do something. So the whole idea here is that we're going to be able to use carbon drawdown broadly to pay for the process of picking up this waste and safely and cleanly putting it on a field to try to enact an agricultural intervention that actually helps people's crops improve in their health and restores some soil function. So this net reaction here is carbon dioxide dissolving in water to make carbonic acid. And then when carbonic acid interacts with the mineral surface, like augite here, you actually see on the right-hand side of the equation here on the bottom that CO2 has been stoichiometrically rearranged to bicarbonate. So effectively, the dissolved inorganic carbon species has been switched from dissolved carbonic acid, so like what's in your Coke when you open it, to a mineral phase. Any other thoughts? All right. Oh, another one that I want to point out is the release of this amorphous silica. I actually think is really interesting, and would be interested to talk to people who are interested in making measurements on phytoliths. Rice actually needs silica to build its body, and it will actively attack rocks like basalt to get at the silica.
What's a phytolith?
Phytolith is a rock made by a plant. So, like rice builds sort of a glassy skeletal structure that's cobbled together out of amorphous silica, and that's called a phytolith.
So the CO2 out there in the top equation is the CO2 that's naturally present in all rainwater from atmospheric CO2.
Yeah, and from the respiration of plants. So that's a good key distinction. Is the counterfactual is that people are going to grow food anyways, and so what you're trying to do is think about how do you actually change the flux of CO2 off the surface while that action is being done. Right. So the real low carbon solution is everyone stops eating. Right. Yeah. I mean, it is what it is, right? Okay. Moving on. So this is my corporate chill slide. But this is how you keep the lights on. And it is nice that they figured out how to keep the lights on here finally. It's a lot different. But essentially, who's gonna buy carbon dioxide removal? Who's even interested in this, right? Like, I don't know if it's something that gets talked about a lot around campus or in these rooms, but in startup space, there's actually quite a bit of buzz. There have been, over the past year, despite some, let's call it negative feedback from the current administration, there have been some pretty big deals signed anyways, right? Where groups like Google or Microsoft or Shopify might have these internal climate goals around offsetting their employees' scope 2 and 3 emissions, and they're actually interested in buying these things to balance their carbon books alongside with trying to decarbonize their operations. Does that make sense? So there's two different things. There's one, you can bring your carbon levels down, but it's actually a different operation to get rid of legacy emissions from the atmosphere, which is considered more difficult in terms of enacting radiative forcings that the planet will respond to actually matters more on a shorter time scale. All right, sold.
What does CDR stand for?
How embarrassing. Carbon dioxide removal. Okay. So, sorry. Take that one as given usually. Yeah, good one. So, and again, just to round out the corporate shill slide, just one company, Microsoft, depending on how you chalk up their spending and how the contracts are actually executed, there's different ways to think about it, but the low end is they spent $2 billion on this last year, right? So we won some money, and that's all good, but it is a small amount of money compared to billions, which I hear are thousands of millions. All right, so this is kind of the board, right? This is where we're playing, and I want you to focus on this India map here. So this little orange blob, that is the Deccan Traps. That is a massive flood basalt in India. And then the color scale here, I would say strictly doesn't exactly make sense, but when you see the darker colors of green, that actually has to do with like farmer density per area. So what you see in India specifically is lots of farmers living really close to the rock source that I'm saying you can use to enact this carbon negative set of reactions, right? And so if we have a carbon negative activity and the feedstock source that is needed to start that carbon negative activity is nearby, we can actually do that more efficiently. So when I say there's carbon drawdown from dissolving the rock, it goes back to this idea of balancing acidity in the pore water. So we had carbonic acid in the water that is balanced by attacking the surface and is rearranged to bicarbonate. This here, I just wanted to introduce some notation. So E is a mass per mass removal potential. So that's basically tells you, hey, if I put down a ton of rock on the ground, how many tons of CO2 can it potentially remove from the atmosphere by neutralizing carbonic acid? And then together with an application rate, so how much rock did I put on the field, and figuring out how much of that rock that I did put on the field actually broke down in the presence of carbonic acid, I can start to make a calculated estimate of what the carbon dioxide removal could be from applying the mineral feedstock to the land, right? So how much could you get? How much did you put down? How much of it dissolved? And then at the end, there's a small fraction that could be lost or not efficiently converted from carbonic acid to bicarbonate in the carbonic acid speciation process. All good?
What's the difference between weathering rate and loss? If it doesn't weather, it might not be lost? Or...
Yes, it's a good question. So it could reverse, right? So I could turn carbonic acid into bicarbonate, but then I could, let's say, have a calcium ion absorb onto a soil surface, I lose charge that into my pore water, and then all of a sudden that bicarbonate has reverted back to carbonic acid. And then that could off-gas. So it's actually a pretty conservative framework for thinking about it from that perspective. It kind of says if reversal, then immediate off-gas. But it's just a way to sort of like get at understanding what can you export at scale from an intervention like this. Does that make sense?
Yes.
Sweet. I'd be very disappointed in myself if I couldn't appease you there. So this is... Yeah.
Why is the weathering rate unitless? Should it be like kilograms per fortnight or something? I don't know.
Kilograms per fortnight? Yeah, so the application rate is your mass per area, and then the weathering rate is a mass fraction, so in between 0 and 1. So it adjusts that number. So the units work out, I promise. Fortnite. At least in India, this is what our enhanced rock weathering deployments have looked like. We have these tractor trailers with these basalt trolleys that drive around and kind of, it's like putting mustard on a hot dog, right? You get the zigzag on there to try and help coverage, and then as rice fields are flooded, the basalt itself is actually worked into the soil. And so I just wanted to get back real quick before I get into the weeds, or the rice rather. There are actually a couple of different ways you could think about those losses, right? So I brought up that you could maybe have complex reactions, downstream evasion of CO2 after your original carbon capture action, but there's also us keeping the lights on, right? We drove the truck. So there are other loss factors that we factor all in. So this is just giving you an idea of the accounting exercise one we have to do to get from gross emissions removals to net emissions removals, right? So we're thinking about the entire stack of actions that we're taking. We're trying to do that pretty seriously. And I would actually argue that we started to do a good job over the past couple of years. Okay, so these are my goals, and I'm just going to keep reminding you what my goals are, so that way we understand each other at least, or hopefully. And so, one, we have an entry point, which is there's a food security issue, and the reason that food security issue exists is smallholder farmers are often working in areas where there's significant soil degradation. If I can go through and I can actually measure a potential climate impact that's valorizable or saleable at the market based on the intervention, then I can go to 3 and rinse and repeat, and I can actually finance climate programs that help people's farming operations, right? So that's the way I want to run it. So this is a picture in Madhya Pradesh of a partnered farmer called Dineshwarya. This is a pretty typical looking field. So it's kind of hard to see because it's so bright in here now, but these right here are these little bundles of baby rice. These are grown in nursery plots. And so what happens is we deploy the basalt in the field is flooded, and then they whip the mud up and they till it so that it gets nice and fluffy and soft, and they can actually go through and they literally transplant these rice plants, plant by plant. And Machi operates in this high water flux environment that's hot, one, because of farmer need, but another reason is because of climate conditions, right? It's a warm place with a lot of water, and the soils are highly weather degraded, so that is a confluence of factors that will help accelerate rock weathering rates in situ. And then because of the outsized impact that you could potentially have working in some of these regions, you actually have pretty strong potential economic adoption drivers for these farmers. This is our current footprint. So mostly India, but there are a few small projects that are happening in Tanzania and Zambia. But we're going to kind of think about this specific set of conditions, these rice fields. And I really like this picture here to the right side. Oh, lights. Should help. Can you see it better now? Problem solved.
Less carbon too.
Yeah, there you go. now we're thinking. But what I really like about this just Google Earth screen grab is if you look at those fields, there's a scale bar down here, and so we're just kind of orienting ourselves for how small some of these areas are, and really how granular we have to be about our data keeping and how we actually process all our data and think about this over very short geospatial wavelengths. And then there's a road that goes through the middle of this map. That photograph is actually taken standing on that road, looking down. So this is what these terraced rice paddies look like, actually, up close in the field. So now I'm going to kind of just walk you through a small study that occurred in central India over the 2004 summer growing season, which is a monsoon-fed growing season. I'm going to submit to you that I think we actually did create an intervention that helped people. I'm going to tell you how I thought we measured that. Talk about the potential for saleable carbon credits, and then, tease you guys with some scientific uncertainties and need for research, because there's still a lot, but we're still getting this framework down in a way that I think is starting to really make sense. So Kharif is the name for the monsoon-fed rice growing season. So if you just wanted to learn a new word today, there it is. Monsoon rice growing season is the Kharif. And the reason that I think it's a good idea to use Kharif as a baseline study is because farmer participation is actually higher. People do grow winter crops in India, but it's only people who can afford irrigation, so that biases you towards the farmers that were already the most wealthy to begin with. And so just for my experiment, this is the tail of the tape for the deployment summary. There were a little over 600 farmers, over 8,000 paddies, over 36 small villages. We deployed 40,000 tons of basalt, and we did that at an application rate of roughly 18.1 metric tons per acre. This is founder and CEO of the company Shantanu. And then this guy here in the middle is called Satvik, and he's developed a bunch of our projects out in the field. And then this guy on the left is Drupad's dad. I only know Drupad. I don't know his dad's name, so I just call him Drupad's dad. So there he is. He came to our company retreat and won every game. So we needed an enterprise resource planning framework to keep all of our data so we didn't lose track of it. And essentially you could think about this as like an interactive ledger that allows me to search data. We named it Matic after Illmatic. I tricked Shantanu into doing that. I'm quite proud of myself, which is why I brought it up. But anyways, so on a field-by-field basis, we can keep track of where we put basalt when, how far did we drive to get there, lots of data and metadata associated with the deployment, so we can walk through that careful accounting exercise that I alluded to earlier. And then the other thing that we can do is we can go on a farm-by-farm basis and try to evaluate how small changes in rice productivity could actually financially impact people. And so I'll kind of try to convince you that we did see some direct evidence and anecdotal evidence of benefits received by these farming partners. And so what I want to do is talk to you about rice yield increases over the counterfactual, right? So counterfactual being like, what would have happened, right, in the absence of our work. So one, we did direct measurements. We prepared trial control plots, and then we did an extensive amount of phone interviews with partnered farmers over the course of actually years. So this university called IGKV in the capital of Raipur gave us sort of the standard operating procedure for how typically are yields estimated in this part of the world. And so for this 2024 Kharif, what we did is we had guys from IGKV show up to the field with this high-tech PVC square. That's exactly a meter. And this is placed in the field, and you carefully harvest within that square, so it gives you a controlled area that you can then convert to, hectares, acres, whatever you want. So we're looking at direct field measurements where this square would be placed in a field that had basalt on it, and then it would be placed in a field that doesn't. So paired control test. And then at the end, the rice crop is dried, and we measure the total biomass and then the paddy weight. The paddy weight is the weight of the grain itself. So that's actually what goes to market. So total biomass going up wouldn't necessarily say a farmer is making a better profit on market from more rice. It's just that there's more biomass. So we differentiate between the two, if that makes sense. Good? Mark gave me a thumbs up. So this is a map of 44 measurements that we, it's really closer because there's replicates, but so this really comes down to about 150 total measurements in these fields in this region where we deployed, and you can sort of see grayed out. Those are the little, those are all of the fields that we actually deployed into, and then where there is a color, that is where there has been a measurement difference for yield that we made. The point is that the delta on paddy weight, so that's rice across this population, was roughly 20%. In some areas, there were actually high flyers on increases in paddy weight. And can anyone guess why?
Better weather conditions?
No, that soil was just more beat up to begin with. So if you go and you work with someone who's got a really, really degraded soil plot that they haven't necessarily tended to super well, the just incremental intervention makes a much bigger difference. So yeah. And then I just sort of wanted to touch on this a little bit. We've kind of built like what's maybe, I don't know, it's quite a large ethnography basically about how did the farmers interact with the people as they deploy, like our employees as they deploy in their land, and how they actually felt about taking their food to market. So we go through and we actually interview in the local language. So this Chhattisgarhi, it's not even Hindi, it's a cooler, harder to understand language. And these folks are sort of essentially telling us what their experience is interacting with the program and in their own words. And then we can compare what did the surveys say to us versus what did our direct measurements say to us, right? And I just want to do a data comparison caveat is that there was kind of no control for the surveys, right? They just say, hey, we think it got this much better, right? it's not something that I can control. But the measured distributions was something that I do think has strong controls. And if you just put it up and do some napkin math, the government has a backstop price for rice. So rice never gets cheaper than a lower level. If you assume that bottom price, and you assume the average acreage in our trial, and the change over our baseline yield that we measured, this looks like it's about $300 in income increase for an average smallholder farmer, which for an average income of just under $1,500 a year is actually a really sizable increase. So about a 20% increase in income at no extra work done by the farmer. And so I'll just give you guys a few quick notes on, all right, how do we keep the lights on? Now we're talking about generating a carbon credit so we can keep bringing the salt to people and hopefully keep yields increasing and be able to intervene with more smallholders and close their yield gap. Any questions before I move on to this sort of second section? Yeah.
So for how many years does it increase the yield? Just for one, or?
So this data all comes from the year after. It does not relax to baseline over the next year, but the first year is the biggest year. What I would say is, if you wanted to compare this to an agricultural process that we do here in the United States, it would be sort of like agricultural liming. So people put ag lime on fields to ameliorate acidity from leftover pesticide, or not really pesticide, NPK fertilizer. I misspoke. But so that is typically done on a cadence of 3 to 4 years. So, you're not going to do it every single year, but dealing with residual acidity in soils is sort of a cropping issue that is well known and well understood. And so that's kind of the model I would use for that in my head here. I did not put that in the conversation. Any other questions? That was a good one. Okay, so this is the same part of the world we were in earlier, but now I want to do a more detailed study in this red box. So inside the red box, I'm going to show you measurements from soil data and the theoretical framework that we've used to try to estimate how much of the salt itself that we put in the field, how much of that do we think actually broke down in situ. And we can do that from looking at detailed soil measurements. So I'll walk through that and then we can discuss. So the theoretical framework here is essentially predicated on the idea that there will be these immobile detrital elements that don't readily move through the soil column, right? So that could be something like titanium, where let's say I go and I measure a soil and I have this black dot, right? This is an amount of titanium and an amount of calcium, let's say. Well, the salt has a lot more calcium and a lot more titanium than the background soil. So if I go and I put a bunch of basalt out on the ground, I create this mixing line. And then I can come back later and I can say, hey, if titanium doesn't actually go anywhere, but calcium is really mobile in these fluid phases, when it rains, when the rock starts to break down itself, then if I'm somewhere beneath this mixing line, that deficit in that cation is proportional to how much of the rock is broken down, which is proportional to carbon dioxide. Does that make sense? None of it will make sense if that doesn't make sense, so we got to make sure it makes sense. Okay, cool. And so we go out and we do paired soil samples. So we'll take a sample before any application is done in the field. We'll have a detailed geochemical assay of our basalt feedstock, and then we come back after application and time and measure this gray point, and then do some inference to back project this gray point to where the white point would be. And then we can calculate an estimation for how much rock has vacated the premises, as it were. All good? Okay, skip that. So this is sort of what the deployment looked like. So again, just wanted to show you on the left side here, that's where we deployed in the field. So all of these different colors represent different quarries that we actually kept track of. And just based on the logistics flavor of the day, this is what showed up on the field when we deployed. And then these dots show you where we were actually able to successfully make measurements. I think this is a really interesting one. There's a river through the middle here, and you'll see that there's a lot of deployment near the river, but we weren't able to make measurements near the river. And that's because the Deccan Tracts, the basalt formation itself is off to the left of this plot, and there's actually a fair amount of erosion that came down the river and gummed up all our measurements, so I didn't claim any of those. Does that make sense? So that was a fun one.
That's the natural process of what you're trying to do.
Yeah. It's just not going fast enough. So I'll make this a little quicker. So we take that paired data, we think about it in the framework of that mixing line, and then a deficit of what are the mobiles to the immobile elements, and then we can come up with a most likely amount of weathering that we think happened across that population of sample pairs. So where I draw your eyes to here, I just think this is pretty, and I'm sad that Jamie Barnes isn't here because I made this like the colors of the San Antonio Spurs throwback jerseys for her, but she just didn't even show up, So, anyways, so this is the on the x-axis. That's the rock addition to the field as we measured. So that's the chemical expression of us throwing basalt into the field, and then the y-axis in this joint posterior tells you where we think the most likely loss of material is based on the ratio of mobile to immobile elements. So that's this spot here. And then I've pulled out the marginal posterior for you because I think it's a little easier to look at. And at the end of the day, the paired samples are telling you that it looks like there's about a quarter to a third of the rock that has actually started to break down in the field. And so then that mass balance can be converted to CO2 weight. And you say, all right, we add all of these things up, and that maximum in the posterior would give you about 1,000 tons of carbon dioxide removal if all of that weathering did happen, and if all of that weathering were converted to alkalinity to draw carbon out of the soil pore space. Does that make sense? Okay, so it was basically 10,000 tons of rock moved, and you get out about 1,000 tons of carbon dioxide credits potentially after 1 year from moving that 10,000 tons of rock. That's the upshot here. And so since we have a simple framework to think about, all right, this is how much carbon could be removed, I wanted to just tease you guys with some potential losses. So this term L here would be inefficiencies. But before that, just in terms of framing this and in keeping the lights on, I think we have demonstrated that there are tangible changes in the rice crop yield partnering with these farmers. And I'm actually cautiously optimistic that if we can sell a carbon credit to, like I was saying earlier, Google, Microsoft, these companies that have expressed interest in it, at these different pricing levels. So right now, companies are typically paying $400 a ton for carbon dioxide removal, where in the future the goal is $100 a ton. And I'm actually saying that even with that lowering price point, because the action we've taken is simple enough and only needs a limited number of measurements, I'm cautiously optimistic that this can pencil out long term and that we can keep doing it. And so even if you take the more conservative number on potential carbon balance by the dissolution of the rock and then just give yourself a 30% loss, you still have about $68,000 worth of carbon credits right there. Okay, so now these are actual geoscience questions. Yeah.
So this is in 1 year, a 10% weathering. Do you expect it to be after that too? I mean,
I think it'll slow down. Yeah, so
exponential decay out.
yeah, I mean, in general, you would expect the most reactive surface sites to react, early, and that you would sort of, if you have a particle size distribution of a powder, you would burn through the finest stuff first. So I would expect each year to be less efficient.
Would you pay for the later years too, or just pay the first year?
You would want to recover the later years, but the sampling cadence that you would need to go to make ex post proof that your intervention had drawn carbon down, that sampling cadence is something you would actually have to think about carefully. Because if you go out and you measure every single year or every 6 months, you actually might push things back into the red because it costs a lot to fire up the plasma on the ICP-OES and ICP-MS.
And they want that verification.
Yes.
Validation.
Yeah. No, there's a lot of longer term questions about how does ex ante or ex post carbon crediting work in doing an intervention such as this. I think we're in very much like a prove it out stage where people want ex post carbon crediting that's very, very measurement, reporting, and verification heavy. But you can imagine a situation in the future once people have seen the ball go through the basket a few times, there might be more of an appetite to do ex ante crediting, and then you could have maybe a partial payout for just doing the intervention itself.
Or just by doing it.
Yeah.
In year 2, you don't reapply more basalt year 2, but they till the fields year 2. Is that going to shake the surfaces enough to?
Could. I haven't measured it directly yet, but yeah, I mean, we haven't reapplied anywhere because we're kind of operating on the 3 or 4 year reapplication cadence, like I described for agricultural line, and then also the demand from farmers has been so high, such that we've tried to reach more people instead of reapplying on people who have gotten it already. Does that make sense?
Very nice presentation, thank you. Interesting stuff. So, the 319 kilograms per ton of deployed basalt, right, is net, if I'm still correct, right?
Yeah.
So, can you explain us a bit more how you estimate the CO2 that you are releasing by picking up a ton of the basalt and deploying it? And have you thought to integrate deployment of the basalt with the activities which are already done? Can you mix the basalt with some material that is already spread, or doing some other activities that are already there, and you don't need to burn diesel to spread the basalt?
So the potential that you asked about, the 319 kilograms per ton, that comes from adding up all of the potential sources of acid balance in the mineral structure itself. Right. So that's kind of an accounting exercise that you get from measuring the basalt feedstock. You get a geochemical assay of what the mineralogy is in the bulk chemistry composition, right?
So you have to subtract what you're burning to do this.
Yeah, and that's what the L terms are.
Right.
And the proportion of L to the rest so the proportion of L to the rest from natural reversals is about 20%. And from us burning things and keeping the lights on, it's about 10%. So I showed you a number where I'd assumed a 30% loss that actually didn't come from nowhere. And I was going to talk about the real losses.
Before you go to your mixing line?
Sure.
Are you assuming one bulk composition for the basalt as your starting condition?
No. No.
So how is that initial starting?
So this is a schematic. This is a drawing that my friend Tom did. But you would just imagine these being sort of more like globular surfaces, and that's why we use the Bayesian framework to think about this, because there's a lot of stuff we just don't know, so we want to keep that flexible. But we built in uncertainty to think about, if we're taking something to Microsoft, for example, and we say, hey, buy this from me, they might say, hey, your pink dot looks all well and good there, but we only want to buy at that orange dot because we don't know if you know enough about your basalt yet. And we say, okay, that sounds like a bad deal, but you're the only buyer in town, so let's go. But that's kind of where this is trending. So you can think with more and more measurements of salt, more and more measurements of soil, you can start to narrow these peaks and actually do something at predictive scale beyond what we have now, which is essentially to do chemistry differences.
Is that the only, are you measuring like alkalinity of the water or like velocity in the water?
Yeah. So we have lysimeters, we have reactive resins that capture cations and anions. Like, we've gone to massive trouble to try to corroborate the monitoring strategies on a smaller scale. When it comes to working with farmers at like the full deployment industrial scale, I think soil sampling is how the primary form of monitoring is going to have to be done.
But have you seen results with your?
Yeah. I have some, didn't make it in because I'm even already running out of time, but I have some reactive resin elution data that's actually like pretty exciting. That it looks like I did some great guesswork, and I basically put a bunch of reactive resin in with like inert glass beads into these small containers, mixed them up, and then said, hey, can I tell the difference between the chemistry of what's eluted off of those resins versus the control field? And you can actually do some highly uncertain but directionally definitely differentiable back calculation of what the bicarbonate flux would have been there.
Yeah, I restate my question a different way. Do you think you could integrate this with some other activities which are already done?
Oh, yeah, so the short answer is like yes. And that was the premise when we did the enhanced rock weathering deployments in the United States. It was just sort of like, hey, you could park this in for agricultural lime. And if you have CaCO3 that's running into nitric acid, boom, that's off gases of CO2. If you put a silicate rock there, you would actually never have the danger of that particular type of emission, and it could actually be a drawback. Here, part of the core premise is that there actually aren't really any helpful activities that are happening without expert intervention. So trying to create a system where there are more sort of modern agricultural inputs is something that we have to build, or that yield gap isn't going to close. But we still do account for it, and I still think it pencils out from a carbon accounting perspective and from a person perspective. If that makes sense.
Yeah, they don't spread anything else.
Yeah, so, there have been folks who've tried to do these types of interventions by replacing lime, and actually thinking about that from an accounting perspective is a huge headache. So, in a way, the project is actually easier because people weren't doing anything to begin with.
So this reaction should be in aqueous phase. So imagine there is monsoon and rain, and in 10 days there is rain, but the rest of the year is completely dry and plants are full. So have you considered that? That maybe in a year there is just 10 days of monsoon and too much water.
So I've been thinking about how water export timescales have the potential to drive, let's say, calcium carbonate chemistry way, way high in certain regions because they're transport limited, and how that could result in off-gassed CO2. So we've been trying to think about the downstream fate of the carbon from the reactions in the pore water and in rivers, and then subsequently the ocean, in a holistic way. Eventually, there's going to be a re-equilibration with the atmosphere, and a lot of the Earth system models right now estimate that bulk loss for CDR is ultimately going to be driven by the oceans, and that's about 20%.
What's ADA?
Eta is the ratio of dissolved inorganic carbon change to alkalinity change. So if you're changing dissolved inorganic carbon to alkalinity efficiently, that's kind of a 1-to-1 stoichiometric carbon dioxide removal, and that would be one. So this is the haircut, so to speak. All right. Another tricky one is you want to make the plants healthier, but they eat some of your cations, and then you lose that as CDR2. Right. So we're taking the accounting exercise very seriously, and also trying to understand how the intervention itself really can potentially help the farmers grow a healthier crop. So I'll just kind of stop there, and then you guys can yell at me.